In this lecture, we continue our discussion on methods of estimation of L and psi of a factor model. Now, in the last lecture, we had discussed about the principal component method for estimation of L and psi, and we had come up to the point of looking at the closeness of comparison of approximating S by L hat transpose plus psi. So, we had stated this result in the last lecture that denoting by delta this matrix which is S minus L hat transpose plus psi, delta ij being the ijth element of this delta matrix. Now, as we had discussed in the last lecture that the way that this L hat and psi is formed, the diagonal entries of S minus L hat transpose plus psi, this element, the diagonal entries will be equal to 0, and only the off diagonal entries of this delta matrix is non-zero. So, since we had approximated S by L hat transpose plus psi, we have that particular observation. Now, under such a situation, we will have this sum of squares of the entries of this delta matrix bounded by the sum of squares of the eigenvalues from m plus 1 to up to p, the smallest p minus m eigenvalues to be the quantity which actually bounds this term here, which is the sum of squares of all the entries of this delta matrix. So, the result states that summation over ij of delta ij squared, this is less than or equal to I equal to m plus 1 to p lambda I hat squared. So, the first thing that we will do in this lecture is to prove this particular result, which gives us a bound on the approximation which we get from the factor the principal component method. Now, first we realize that the diagonal entries of delta matrix are 0, and thus the sum of squares of entries of S minus L hat transpose minus psi, this is less than or equal to the sum of squares of entries of this S minus L hat transpose, because we are going to have the diagonal entries of these to be equal to 0. The diagonal entries of S minus L hat transpose are non-zero, and hence the sum of squares of of all the entries of S minus L hat transpose minus psi will be less than or equal to the sum of squares of entries of S minus L hat transpose. Now, if you look at this left hand side here, that is nothing but trace of delta square, which of course, as we have denoted, that is equal to double summation over ij, this delta ij square. So, this is less than or equal to sum of squares of entries of this S minus L hat transpose matrix. Now, we will look at what this sum of squares entries of S minus L hat transpose is, and then we will have that quantity to be equal to this upper bound. Now, let us look at how we had defined S through the eigenvalue eigenvector pairs. So, S as it was defined, it is lambda 1 hat E 1 hat, then this was of order p. So, this is lambda p hat E p hat, this into the transpose matrix, which is lambda 1 hat E 1 hat transpose, and the last entry being lambda p hat times E p hat transpose vector, right. That is, this S is equal to lambda 1 hat E 1 hat E 1 hat transpose plus, I will just write this mth term here, the mth term is lambda m hat e m hat transpose, this plus lambda m plus 1 hat e m plus 1 hat e m plus 1 hat transpose, 2 up to the last term, which is lambda p hat e p hat e p hat transpose, right. Now, if we look at this part here, there is a reason why I have written all these terms here up to m and beyond m. So, if we look at the first m terms, these first m terms are going to come if we look at L hat transpose matrix. In other words, this S can be written as, this is the first m terms contribution to S is basically L hat transpose, this plus, I will just put it as a sum, summation j equal to m plus 1 to up to p, this is lambda j hat e j hat into e j hat transpose. So, this will imply that this S minus L hat transpose, this matrix is equal to the terms which we have neglected, assuming that lambda m plus 1 to up to lambda p, they are having a negligible contribution. This is lambda j hat e j hat transpose. So, we have this S minus L hat transpose to be given by this right hand side here. Now, we will use this form of S minus L hat transpose in the previous equation, sum of the squared entries of S minus L hat transpose. Now, this of course is a symmetric matrix. So, what we are going to have is that this trace of delta square from the previous equation is less than or equal to trace of this S minus L hat transpose, this square. Why is that so? Because we are looking at sum of squares entries of this symmetric matrix, and hence we are writing that in terms of the trace of this S minus L hat transpose square. Now, what is this equal to? Let us look at what is the trace of S minus L hat transpose square matrix. This is trace of, I will just write the two matrices L hat transpose, this into S minus L hat transpose. Now, we will plug in the value of S minus L hat transpose as in this expression here, and then we will be able to write it as, this is summation over j equal to m plus 1 to up to p, this is lambda j hat e j hat times e j hat transpose. So, that is this matrix, and then product by the same thing here, j equal to m plus 1 to up to p lambda j hat e j hat times e j hat transpose, right. Now, if we look at this particular product here inside the trace, what is going to happen is that we recall that this E1 hat, E2 hat up to EP hat, they are orthonormalized eigenvectors corresponding to the eigenvalues, and hence if we are looking at a particular j here and a j prime in this summation, then the product will make that product will be equal to 0, because we will be looking at multiplication of E j hat prime times, if we look at another j prime here, then it would be E j hat prime multiplied by E j prime, and that would be equal to 0, because the vectors are orthonormal, and hence only the terms for which the same index in this sum and the same index in this sum are multiplied, and that would lead us to the following expression, which is summation j equal to m plus 1 to up to p lambda j hat times this E j hat E j hat transpose times the same quantity from the other summation, same index. So, that is lambda j hat times E j hat times E j hat transpose. Now, all other terms for which the indices in these two summations differ, they will be equal to 0 because of the orthogonal properties of these E j vectors. So, what do we get after this multiplication? This lambda j hat anyway is a scalar. So, this E j hat transpose E j hat, that would be equal to 1 because we have E j hat vectors to be orthonormal. So, this is nothing but trace of the matrix which is j equal to m plus 1 to up to p lambda j hat square E j hat transpose. Now, we will take the trace some term by term, because trace of the sum is sum of the traces. So, lambda j hat square anyway is a scalar quantity. So, we take the trace straight away inside, trace of E j hat times E j hat transpose, and furthermore the trace of A b equal to trace of B a. So, what we are going to have is summation j equal to m plus 1 to up to p lambda j hat square trace of E j hat transpose E j hat, and that is equal to 1. So, what we have is this summation to be just equal to j equal to m plus 1 to up to p lambda j hat square. So, this would imply the desired result, that trace of delta square, which is summation double summation I j delta I j square, that is less than or equal to the term that we have got in here. So, that is summation j equal to m plus 1 to up to p lambda j hat square. So, this proves the result that this is quantifying the closeness of approximation, that this matrix, which is the difference between S and the matrix which approximates S in this principal component method for estimation of L and psi, that this is bounded by this quantity on the right hand side. So, after proving this particular result, we move on further and look at another aspect of this principal component method for estimation of L and psi, which will give us idea about the contribution of factors to total sample variance. Now, in order to see the type of contributions that a particular factor would be having, contribution of factors to total sample variance, we recall that in this principal component based method, we have this SII to be equal to summation Lij square, Sij equal to summation Lij square, j equal to 1 to up to m, this plus Lij hat square actually, this plus psi I hat. So, this is what is the expression for approximation, that we are going to approximate SII by this particular term, and from here we can say that the contribution of the first factor to SII is going to be given by, now if we look at this particular term here, this is Li1 hat square, Li2 hat square and so on up to Lim hat square. So, the contribution of the first factor is related to the term for which j is equal to 1 in this expression. So, what we are going to have is that it is Li1 hat square. Now, if we look at the total sample variance and then the contribution of this first factor to the total sample variance, Now, what is total sample variance? Total sample variance is trace of the S matrix, which is equal to S11 plus S1 S22 plus up to SPP. This is a p dimensional random vector that we are considering. So, the contribution of the first factor to the total sample variance would be from these expressions. So, we will have that contribution to be equal to L11 hat square. So, this is the contribution of the first factor in S11. Similarly, the contribution of the first factor to S22 would be given by this expression. This is L21 hat square and so on, this up to the contribution of the first factor on the pth component, that is SPP, would be given by L hat, this particular term. So, this is the total contribution of the first factor to the total sample variance, which is given by trace of S, which is a summation of SII's, I equal to 1 to up to p, is this particular quantity. Now, it is interesting to see what this term is actually equal to. If we look at the L hat matrix in this principal component based methods, this L hat, which is of the dimension of L by p, p by m, this is given by root over lambda 1 hat E 1 hat and so on. This is truncated up to the mth term, the number of factors. So, this is lambda m hat times E m hat, right. So, if we look at this, then the jth column here is this. The jth column is, say I write that as L 1 j hat, L p j hat. Now, that is equal to root over lambda j hat times this E j hat vector. So, we have this as the jth column. Now, if we look back at this contribution term, what we had got, this was the contribution of the first factor to the total sample variance, which was L11 hat square, L21 hat square, LP1 hat square. So, for j equal to 1, what we are going to have is the first column of this L hat matrix, and that is nothing but L11 hat up to LP1 hat. Why are we looking at this particular expression? Just to identify that this contribution of the first factor to the total sample variance is nothing but sum of squares of the entries of the first column of this L hat matrix. This is the jth column. So, in general, if we consider any j as in here, this summation, which is L I j, summation I equal to 1 to up to p hat square, that is this, the norm of this particular vector is going to be given by root over lambda j hat E j hat, this multiplied by its transpose, it's lambda j hat E j hat transpose. So, what is this is equal to, because this is E j hat transpose. So, we will have this transpose is on the other side. So, it is root over lambda j hat E j hat transpose into root over lambda j hat E j hat. So, this is going to give us this lambda j hat, and this is E j hat transpose times E j hat. They are orthonormal, and then this is going to be just equal to 1. So, that this particular term is equal to just lambda j hat. Now, this will imply that the expression that we previously got as the contribution of the first factor to the total sample variance is this term is just going to be given by lambda 1 hat, because it concerns this first row here. So, for the particular value that this is L I 1 hat square for I equal to 1 to up to p, this term is nothing but lambda 1 hat. So, this is the way in which actually the contribution of the respective factors to the total sample variance can be calculated. Now, using that we can further say that the proportion of total sample variance explained or captured through first factor is going to be given by lambda 1 hat divided by this trace of S, which is going to be that summation, which is lambda 1 hat divided by summation of S I terms I equal to 1 to up to p. In a similar way, the contribution of say k factors, the first k factors can be defined. So, this also can be extended. So, the proportion of total sample variance explained by first k factors would be given by the first k factors would be associated with the first k eigenvalues. So, this is I equal to 1 to up to k, this divided by summation I equal to 1 to p S I and so on, right. So, this gives us a way actually from the principal component based method that how we can actually quantify the contribution of different factors in explaining the total sample variance, which was the basic objective actually to capture the variance covariance structure, and as a byproduct we are looking at these outputs. That will conclude this method of principal components. Now, we will look at another method of estimation. Method of estimation of L and psi. This is the first method that we had discussed was the principal component method. This is method number 2. This is maximum likelihood estimation. Maximum likelihood estimation of L and psi. Now, once we say that it is maximum likelihood method of estimation, we would require certain distributional assumption on this the random variables concerning the system, and we will have to impose certain conditions, certain distributional assumptions. Now, suppose from this m factor model x minus mu equal to LF plus epsilon, we have the joint distribution of the random vectors involved on the right hand side. Just recall the dimensions. This is p by 1, this L is the factor loading matrix, p by m, this is the vector of m common factors, and this is the vector of p specific factors. And suppose we have the joint distribution of f m dimensional and that augmented with epsilon vector, which is p dimensional. So, this entire vector here, which is m plus p dimensional random vector, suppose the joint distribution of this is an mp dimensional multivariate normal with a mean vector as a null vector, and the covariance matrix naturally has to satisfy the structure of the factor model. Now, in the factor model, this f vector, which is the vector of the common factors, it has got a covariance matrix to be an identity matrix, and then the covariance matrix of this epsilon vector, the vector of specific factors, is having a diagonal structure which is psi matrix, and the covariance between f and epsilon in such a factor model needs to be a null matrix, and hence we assume that the joint distribution of f and epsilon has got this m plus p dimensional multivariate normal with the mean vector 0, and this as the covariance matrix, right. Now, this would imply that our x minus mu, which is LF plus epsilon, this can be written as L times an identity matrix of order P, this multiplied by this random vector, this f and epsilon. So, if you multiply this, what we are going to get is LF plus this epsilon vector. Now, if we denote this m plus p dimensional random vector by y, we have a result from multivariate distribution theory that if y follows a multivariate normal, now this is a matrix of constants. So, this will, the distribution of this will also be a multivariate normal of the order that is determined through this. What is the order? This is p by m and this is a p by p, right. So, this has got p rows and m plus p columns. So, the order of this matrix, which is L augmented with I p, is p rows and m plus p columns, and hence the dimension of this x minus mu vector multivariate normal, it will be a multivariate normal distribution n p with a mean vector given by this multiplied by the expectation vector of f and epsilon. What is that? That is a null vector. So, this is a null vector and a covariance matrix which we are going to calculate. Now, the covariance matrix, this covariance matrix of L I p, that multiplied by f epsilon, this is going to be given by, this is a matrix of constants. So, this is going to be given by L I p multiplied by the covariance matrix of this. Now, the covariance matrix of this is I m null null psi. So, what we are going to get, this is I m null null matrix psi matrix, and then the transpose of this is going to come here. So, that is L transpose I p, right. Now, if we take the multiplications, what we are going to get is that this multiplied by this is going to lead us to L, and L I p multiplied by this is going to give us psi, and then this is L transpose I p. So, what do we get? We get L L transpose plus psi. Now, what is L L transpose plus psi in a factor model? That is nothing but the sigma matrix. So, we can fill in this particular dot here and say that our x minus mu has got multivariate normal p dimension with mean vector 0 and a covariance matrix equal to sigma. Well, you have the covariance matrix of sigma straight, covariance matrix of x straight away equal to sigma anyway, but we had derived that covariance matrix of this LF plus epsilon through the multivariate normality distribution of this augmented f with epsilon vector. Under the assumption of joint multivariate normality of f and epsilon vector, what we have realized is that this x minus mu has got a p dimensional multivariate normal with the mean vector 0 and a covariance matrix as sigma. Now, we are in a position to frame the likelihood estimation, because we can now write the form of the likelihood function for observation vectors x1, x2, xn, for observation vectors x1, x2, xn. The likelihood function is given by let us denote that likelihood function as L. Now, this is going to be written as a function of mu and sigma given the data x1, x2, xn. So, given x, this is going to be given by 2 pi to the power minus np by 2. Why it is that? Because we have random sample of size n and we have each of the random samples a multivariate normal with dimension p. So, for each of these random samples we will have a 2 pi to the power minus p by 2, that is the dimension of the multivariate normality, and we have n such terms, and hence we have this factor as 2 pi to the power minus n by 2, and then we will have a determinant sigma to the power minus n by 2. From where does this come? If we once again look at the structure of multivariate normal, in the density of each of these we will have determinant of sigma to the power minus half, and since we have n observations we will have this actually leading us to determinant of sigma to the power minus n by 2, that multiplied by the exponent. Now, we will straight away write the form of the exponent that we usually use, which is minus half trace of sigma inverse A, this minus n by 2 x bar minus mu transpose sigma inverse x bar minus mu, right, where this x bar vector is 1 upon n summation x I vectors. So, it is the sample mean vector obtained from the observations x1 vector, x2 and up to xn, and this A matrix. This is actually the formulation of calculating the maximum likelihood estimators of multivariate normal distribution. So, that this A is j equal to 1 to up to n x j minus x bar vector into x j minus x bar vector its transpose. So, this is the standard form that we will have this as the exponent of the joint distribution of x1, x2, xn, each of them having a multivariate normal distribution, having a multivariate normal distribution with the order of the multivariate normality as p. Now, if this is the likelihood function, we can also write the log likelihood function. Let us denote that by small l. This is L mu sigma given this x1, x2, xn, or in short just to as we had written as x here. So, that is going to be equal to minus np by 2 log 2 pi, this minus n by 2 log determinant of sigma, this minus half trace of sigma inverse A minus n by 2 x bar vector minus this mu vector transpose sigma inverse x bar minus this mean vector mu, right. Now, from this expression here, what is the basic objective is to get the maximum likelihood estimators of L and psi, right. That is what we are aiming at. So, in order to get the maximum likelihood estimators of L and psi, we will write this log likelihood function in terms of those. Note that although we have written the log likelihood function of mu and sigma, it is in this particular sigma that we have L and psi, and hence this can be written in terms of log likelihood function in terms of L and psi given x1, x2, xn. This is going to be minus np by 2 log of 2 pi minus n by 2 log of determinant. Now, here we are going to use the fact that sigma, here we had the determinant of sigma here. In place of sigma we will write L L dash plus psi. So, this is L L dash plus psi, determinant of this matrix, this minus half trace of sigma inverse A. So, this is L L dash plus psi whole inverse times that A matrix, this minus n by 2 x bar minus mu transpose sigma inverse, that is L L dash plus psi whole inverse times this x bar minus mu. So, what we have done is to look at this log likelihood function. This was as a function of mu and sigma. We transformed that actually using the factor model just by replacing sigma by the corresponding L L dash plus psi quantity. So, we have this expression which is star as the log likelihood is the log likelihood function of this mu L psi given the observation set, that is x1, x2, xn. The choice of L is not unique, as we have seen in the M factor model, that the choice of L is not unique, and as such we need to impose certain additional conditions in order to make L unique, and that is the type of condition which is used in order to maximize this, subject to the conditions which would make L to be unique. So, we write this, that since choice of L is not unique, we impose conditions like L dash psi inverse L equal to a diagonal matrix to make L choice of L unique, and then maximization of star subject to the imposed condition L dash psi inverse L equal to a diagonal matrix gives the maximum likelihood estimators of L and psi, with of course mu hat the maximum likelihood estimator to be given by the usual maximum likelihood estimator, which is x bar. So, using the form star as in here to be the likelihood function of mu L and psi, and using a condition like this to be a given diagonal matrix, we can maximize the star with respect to this condition and arrive at the maximum likelihood estimators of L and psi with mu hat maximum likelihood estimator to be given by x bar. Now, there are other methods of estimation of L and psi when we are talking about the factor analysis model, but we have in this course looked at two such important, most widely used methods of estimation of L and psi. The first one that we had discussed was the principal component based methods, and the second one in a more general setup when we are looking at maximum likelihood method of estimation. So, we will conclude this estimation part here. And to conclude, actually we will just look at one small note which is important, which gives us a large sample test, large sample LRT test for the number of common factors. So, what we are going to address is the following fact, that the number of common factors as such is not known to us, and what is the best way to judge what is the number of common factors that should be used in a particular X vector model. We look at a large sample likelihood ratio test. Now, we are doing this because we have just now actually obtained the maximum likelihood estimators of L and psi, and this large sample likelihood ratio test is based on that maximum likelihood method of estimation. Now, what we are doing here is that we are saying that a null hypothesis is of the form that sigma is equal to L dash plus psi, with the order of L to be p by m with a chosen p here. Suppose our interest is to test this null hypothesis against the alternate hypothesis that sigma is any other positive definite matrix, any other positive definite matrix. So, we are going to test this. If the null hypothesis is accepted, then we take this m to be the number of common factors as in here. Now, for certain m, as we will see that this might actually get rejected, and then we will accept that that particular choice of m does not hold good for the given observation vectors x1, x2, xn. Now, this testing is to be carried out using the data as in x1, x2, xn. So, based on these n data vectors, we are going to test this null hypothesis against the alternate hypothesis HA using the LRT philosophy. Now, the likelihood ratio, as we know, likelihood ratio is going to be given by, this is supremum over script theta naught of the likelihood function. Now, this likelihood function will be under the null hypothesis, meaning thereby we will have mu L psi given this x, the entire data vector, that divided by supremum over script theta. Now, when we talk about script theta, it is with respect to not this factor model, it is with respect to the mean vector mu and sigma being any positive definite matrix. So, we will have to compute this particular term, which is going to be called the likelihood ratio when we are looking at testing of this null hypothesis, and then we will use standard large sample theory of likelihood ratio in order to formulate this testing of H naught against H A. Now, in order to do so, what we would require is these two supremum quantities. Now, in the unrestricted setup, mu hat maximum likelihood estimator is going to be given by x bar, that we have already seen time and again, and this sigma hat MLE is going to be Sn, where Sn is nothing but 1 upon n summation xj minus x bar into xj minus x bar transpose j is equal to 1 to up to n. So, that is the maximum likelihood estimators in the unrestricted setup. So, this will actually look at the denominator part, and then in the likelihood function we will have to plug in these values of mu as x bar and sigma as Sn, which is of this particular form, and then we will be able to write this supremum over script theta, the entire parameter space. Now, what is the entire parameter space? The entire parameter space, just to recall, the script theta is the set of all mu and sigma, wherein this mu belongs to r to the power p and sigma is positive definite. So, that is my script theta. So, supremum over script theta of L mu sigma, I will just drop this x. So, this is going to be proportional to, I am ignoring the constants. So, it is supremum over theta L mu sigma, that is going to be given by determinant of S n to the power minus n by 2 e to the power minus n p by 2. And this we had of course done when we were looking at maximum likelihood method of estimation in multivariate normal and testing, but if one wants to recall why it is so, you will have to look at this expression here. So, this is basically the likelihood function. You plug in mu hat equal to x bar. So, this term would be equal to 0. So, plugging in mu hat equal to x bar, this will be a null vector multiplied by whatever sigma hat you plug in, this is going to be that, and this A is this matrix which is n times. So, this A is nothing but n times S n. So, we will have in place of sigma inverse n times S n inverse being plugged in, and what we are going to get is the expression that I had written here. So, supremum over theta L mu sigma is going to be proportional to determinant of S n to the power minus n by 2 e to the power minus n p by 2. Now, suppose L hat and psi hat are the maximum likelihood estimators of L and psi under script theta naught. Now, how we are going to obtain this L hat and psi hat? That is using the method of maximum likelihood estimation that we have just now touched upon. So, using those that technique in order to get to this L hat MLE and psi hat MLE under H naught. Under H naught, how it is going to matter? Under H naught we will have a fixed m here. Now, for that fixed m we will actually look at the m factor model, and then that is going to determine that this L hat MLE and psi hat MLE are going to have the dimensions as what is specified through the null hypothesis, that m factor. Now, along with that we will have mu hat MLE irrespective of this L hat psi hat, that is always going to be equal to this x bar term. Now, if L hat is the maximum likelihood estimator of L and if psi hat is the maximum likelihood estimator of psi, we will have the maximum likelihood estimator of sigma hat by invariance property of the maximum likelihood estimator. We will have this as L hat transpose plus psi hat, where this is the maximum likelihood estimator as we have given in here. This also is the maximum likelihood estimator, right. Now, we are in a position to write this supremum over script theta naught of the likelihood function. Now, this likelihood function will be in terms of mu L psi, this given x, I will just drop it. Now, this one is going to be proportional to terms similar to this. Now, this is determinant of sigma in the likelihood function. Now, sigma is estimated by sigma hat, which is L hat transpose plus psi hat. So, this is going to be proportional to L hat transpose plus psi whole to the power minus n by 2, and here the exponent terms do not cancel out and give us a nice form like the previous one. This is going to be a bit complicated because terms do not cancel out. The second term of course will be equal to 0 because it is x bar minus mu. So, mu hat being equal to x bar will lead the second term to be equal to 0. However, the first term is going to be trace of L hat transpose plus psi hat, this is sigma. So, trace of sigma inverse is this times that I will just write this as A, because it is better to write that as, no, if we write that as A, then this term will be given by this Sn, right. So, we have this particular term here. So, n times Sn is basically A, and we have the supremum over script theta of the likelihood function given by this. So, we can formally thus write the likelihood ratio. So, this will imply that the likelihood ratio lambda is supremum over script theta naught of L mu L L mu L and psi. This L is corresponding to the factor loadings, supremum over script theta of L mu sigma. So, that this term we can look at what terms we had got earlier, use this form here and use this form here in order to write this particular likelihood. And so, we can use this form and this form here in order to write the final form of this likelihood ratio using asymptotic theory. Using asymptotic theory, we know that this lambda or minus 2 log lambda, this follows asymptotically a central chi-square on the degrees of freedom, which is dimension of script theta minus the dimension of script theta naught. So, we will look at this likelihood ratio, and then using the asymptotic theory, we have minus 2 log lambda following asymptotically a chi-square central with degrees of freedom as dimension of theta minus dimension of theta naught. From a given data, we will obtain what is the observed value of lambda, what is the observed value of minus 2 log lambda, and looking at the appropriate degrees of freedom of that central chi-square, we will actually look at acceptance or rejection of the null hypothesis. So, what we are going to require this particular number here. So, what we see is that dimension of script theta. Now, script theta was this space here. So, this has got p entries, and the number of distinct elements of sigma is going to be the dimension of this script theta. So, that this is equal to p for mu and p into p plus 1 by 2 for the sigma matrix. Now, if we look at the dimension of script theta naught says that this sigma, so this h naught is what we have giving us L dash plus psi. Now, the dimension of script theta naught, it still has the components of mean vector. So, that is p of them, and then we will have the elements here and the elements here, which are going to give us, this is Pm. Pm is the number of terms corresponding to the factor loading matrix L. This plus the p diagonal entries of psi are going to give us this. Now, the dimension of script theta naught is something less because of the type of restriction that we had imposed. Now, this is thus going to be the number of restrictions, which is this. Now, what is or how is this one coming? This basically is coming that from the number of restrictions as we take MLE under script theta naught with the restriction of a diagonal matrix. So, since we have the diagonal matrix of that m by m matrix, which is you can just go back a little bit. This is basically the restriction that we plug in. So, this L transpose psi inverse L, this matrix is a diagonal matrix, and hence these are the number of restrictions that we have in computing the maximum likelihood estimators, and hence we will have the dimension of script theta as it is given by this, and the dimension of script theta naught to be equal to this. So, there is no problem in computing the degrees of freedom of this central chi-square, which is the asymptotic distribution of minus 2 log lambda. So, we will thus reject null hypothesis. Now, if we look at this likelihood ratio, this is the likelihood ratio. So, when we are going to reject the null hypothesis, if this particular contribution with the numerator term supremum over script theta naught is too small with respect to supremum over script theta, then we usually reject the null hypothesis. So, we will reject null hypothesis if observed minus 2 log lambda is less than the cutoff at a fixed level of significance. So, that concludes actually this testing procedure, which was based on the maximum based on the large sample theory of the likelihood ratio test for the number of common factors that we will be choosing in an M factor model. So, that concludes our discussion with about the factor analysis. There are other concepts in factor analysis like factor rotation, which also occupies an important place, but we will end the concept of factor analysis here. From the next lecture, we will look at the canonical correlation analysis.